So we're ready to start a whole series of calculations involving equilibria. In some instances, and we've already done some problems like this, we will be getting the equilibrium concentration and obtain the equilibrium constant from it. And in the other cases, we will be given the equilibrium constant, K, and we're going to try to calculate the equilibrium concentrations. We haven't seen anything like those types of problems before. So let's just take off running. Okay, here's the first one. Now in this problem, we're trying to calculate the Kp value. So the first thing I would always do when I'm trying to get a value for Kp is to write the expression. So I look up there at the balanced equation. I see that they're both gases, so I will include them both in there. It would be the pressure of the product, which is NO2, and it's squared, okay, so it's raised to the power of its coefficient, divided by the pressure of N2O4. So my goal is to know those two values, plug them in, and I will know a value for Kp. Now let's write the reaction down so that I can write under it and practice using the ICE table that I taught you about before. Now in this ICE table, we'll start with the I, which we know stands for initial. We read the problem and it says an initial pressure of N2O4 is 0.152, 0.152. I said it right. And that is all that's placed in the reaction vessel. If that's the case, then there is none of this. And it tells me the total pressure is 0.209. Well, this is a change for the reaction taking place, and E for what's there at equilibrium, but there's no place in here to put a total pressure. So I can't put any other numbers into my table. So what I want to do at this point is use a variable to represent this change taking place. I know from the balanced equation that every time one of these reacts, I'm going to make two of those. So let's let X represent how much of this reacts. We don't know how much will react, but we know some of it will, and I just call it X. The change line is the reaction taking place. So every time X of these reacts, 2X of this is going to be produced. So I represent that with a 2X. Now you need to possibly pause this and think about what I just did. The change line is this reaction taking place. The I line has not got a 1-to-2 ratio. The E line doesn't have a 1-to-2 ratio. But the change line is the reaction taking place, and that is incorporating those coefficients. So here we have 0.152 minus X, because I'm taking this and doing the change to it. And this is 0 plus 2X, and we have that. Now if I put this up here in my equilibrium, I'm not going to get a value for Kp because I have this variable in there. Somehow I need to get rid of this variable so I can plug numbers into my expression to obtain a Kp. So I look again at what's given to me. It says that when equilibrium is reached, the final total pressure is 0.209. Well, here is the pressure at equilibrium of N2O4. This is the pressure at equilibrium of NO2. The total would be the sum of those two things, and that has to equal 0.209. So now I could solve for X. I have 0.152, combine my X terms would be plus X, is equal to 0.209. So X is 0.209 minus 0.152. That's going to give me an X value equal to 0.057. And these was all plugged in as pressures in atmospheres, so that's what I have here is X in terms of atmospheres. Now, what do I do next? I need to know the pressure of these two guys. So I'm going to go to my E line and right here be able to get the pressure of N2O4 at equilibrium. So the pressure of N2O4 at equilibrium would be 0.152 minus X, which I established was 0.057. That is going to give me a pressure of 0.095. Okay, so why did I want to know that? Because I need to know it up here. So I can put it in this expression. And then I need to know the pressure of NO2, and that is 2x. So the pressure of NO2 at equilibrium is 2 times this 0.057. And that is a value of 0.114. Okay, and I can put that in here, 0.114, the pressure of NO2, and that's squared. So when I put those values into my calculator, I have 0.14. I can only know it to 2 significant figures because I only know this 2 significant figures. Let's back up and see why I can only know that to 2 significant figures. X. When you're subtracting, you can always keep the least number of places to the right of the decimal point. When you're subtracting, you keep the least number of places to the right of the decimal point. There are only 3 to the right, which is 2 sig figs. But the rule for division is you keep the least number of sig figs, and so that's 0.14. Okay, so our previous problem, we were trying to obtain the value for K. Now I see a series of instructions where if you know K, you can determine the equilibrium concentrations. So let's just talk through each one of these, and then we'll do several examples of it, okay? There's a basic outline to follow. Some of this you'll be familiar with. We're going to use an ICE table. You will have to use a variable in your change line to represent the change in concentration that's taking place. Then you're going to write your equilibrium constant expression. That's what it says in number 2. Now what do I mean by that? That's the law of mass averages that we talked about earlier. So you'll write that out. And you'll take that E line and plug it into that expression. You'll solve for X. And X is not necessarily the answer. X might be something you have to do to it to obtain the value of those concentrations. So keep that list of instructions handy, and let's work through a problem. Now, I'm going to have one other thing pop up here. This section is very important. We're going to learn how to do it in general for various reactions in this chapter. Then we're going to look at it in the acid-base equilibria environment, and then we're going to look at it in another environment in a later chapter. So we are going to be doing this process many times over. And it's very important that you turn your brain on and really concentrate through each one of these, because there is no one set procedure. I have a general outline of what to do, which I'll get it back up here, general outline what to do, but each problem is going to have variations that kind of follow this theme. So I recommend that you practice, practice, practice. Redo the problems I have here, do ones in the book. Really focus in Sapling in your homework, your online homework system, on being able to work the problem without just looking for a solution, because you have got to develop the skills of setting them up. Okay, so here we go. Notice here I'm giving you a K value, a KP value of 1.80. Now if I'm given a KP value, I like to go ahead and write the expression. Kp would be the pressure of PCl3, these are the products, right, times the pressure of Cl2, products over reactants. We have PCl5, and they're all raised to their power, their coefficients. And it wants us to do all this work and determine PCl5, and I got to have another P in there. Let's do this. Let's make a big P and a subscript of PCl5. I got too few P's in that one. Okay, so we're trying to determine the pressure of PCl5. Somehow I will use this, and let's see how we do it. We write the reaction, I will write the reaction so that I can put an ICE table underneath it. So here's the reaction, PCl3 plus Cl2. Okay, there's my reaction. I've got room for an I, that's initial, C, that's change, E, that's equilibrium. And then I look and see what's given to me. They put sufficient PCl5 into the reaction vessel to give an initial pressure of 2.74. So that's all they're telling me they're putting into the vessel. Now keep in mind that when you're doing KP, you must deal with atmospheres. So if the problem didn't give it to you in atmospheres, you must convert it to atmospheres. So now we know the pressure of PCl5 initially. And that's all they said they put into there. So we will know that these are 0. There isn't any. I look through there and it gives me a value for this KP of 1.80, but otherwise there's nothing else for me to fill into my table. They didn't give me equilibrium values to put in there. If they did, I'd put in what they gave me, but that's it. So at this point, I know I must use a variable to finish my table. I never go to that variable if there's other things that I can fill in and I can put numbers in instead of variables. But there isn't anything else, so I know that every time one of these reacts, there's a 1 coefficient. Every time one of these reacts, you're going to make one of these and you're going to make one of these. So if X reacts, I'm going to produce these amounts. So now I have 2.74 minus X, I have X, and I have X. So now I have my E line, and I'm ready to take that E line and plug it into what I see here. So 1.80, which is what this equals, right, is equal to PCl3, which is X, Cl2, which is also X, and X times X is X squared, divided by PCl5, which was 2.74 minus X. Now we have to solve for X. How do we do that? Well, let's just start working it, and I'll come down here where I've got a little bit more room. So I'm going to multiply this whole denominator and get it over here. I'm multiplying both sides basically by the 2.74 minus X. Then I'm going to do the distributive property, right? I'm going to take this times the first term and this times the second term. When I multiply by the first term, I get 4.932. I'm carrying extra sig figs along for the ride. I really only know it to 3, but I'm just keeping a little extra in there. And then this times the negative X is a negative 1.80X is equal to X squared. Right, now what we have to do is we need to get it in the form where 0 is equal to X squared. I'm taking these terms over to this side, so plus 1.80X, bringing this over, minus 4.932. Now I recommend that if you don't understand what I'm doing, you pause and try to see how I got from here to here. Now what is this in the form of? This is in the form of, that's a 0, ax squared plus bx plus c is equal to 0, and that's the quadratic. And then to get the x value using the quadratic, okay, it's a negative b plus or minus the square root of, did you think you were allowed to forget this equation somewhere along the line? B squared minus 4ac. I remember learning it in my algebra class, and let me tell you, that was a long time ago, all over 2a. So we can plug in our values. B is the 1.80. It's a negative b, plus or minus the square root of b squared. That's 1.80 squared. Okay? I'm going to make my pen work a little bit more here. Let's see if I can get some ink flowing. A little bit better. Okay. B squared minus 4 times A, which was 1, times C, which is a negative 4.932. Okay, all over 2A, which was 1. Okay, so we keep working. Now there's lots of places you can make mistakes here, aren't there? That would end up giving me, and I'll see if I can see my numbers a little bit better here. I want to get what's underneath that quadratic. It's a negative, not underneath that square root term, 1.80 plus or minus, the value is 4.79 over 2. Okay, so if I take this plus 4.79 divided by 2, I will end up with a value of x, which is what I'm solving for, equal to 1.49. Now if I do the minus, I'm going to get a negative number, okay? You can't start with this and subtract a negative number because that means you're producing more. So that term, the minus one, negative 1 minus this value, that is not going to be a legit value. And that will always be the case. There is a plus or minus here, and one of them will be a legitimate value. The other one would be not good. And the negative one would be not good. Okay? It seems like almost every time I do it, the added one is the one I want. But it may not be the case, but I do know that only one of them will make sense. So now I have x. When you get x, don't assume that's the answer. Very often a student on a test will plug in 1.49 and say, hooray, I'm done. But always when you get x, don't assume x is the answer. Go back to the question and say, what is the question asking? Calculate the pressure of PCl5 at equilibrium. So we need to know this value right here. Okay, what is this at equilibrium? Well, it'd be 2.74 minus the 1.49, my x value. And when I subtract those, I'm going to get 1.24. Now, what would the units be? These were all plugged into here in atmospheres. Okay, so that is the value of the pressure of PCl5. Now, PCl3 and Cl2 is x. So this is the pressure right here, the pressure of PCl3 and the pressure of Cl2. But it's not the pressure of PCl5. Okay, we've got another one to work. The previous problem used the quadratic. We're going to look for every trick possible not to have to do the quadratic. Sometimes you will be forced into it, but there are a couple things to look for so that you won't have to, and this has one of those things. So let's work through this one. In this problem, I have a Kc value, and I'll go right ahead and write the Kc expression, right? Kc, I'll just get really in the habit of writing these all the time. Now, it's in terms of concentration instead of pressure, so it's the H2 concentration, the I2 concentration, divided by the HI concentration, all right? And we know the value of this is 0.0156. So that's one thing that I know already. And I can go ahead and write my reaction so that I can do an ICE table under it, because this is almost always, not always, but almost always, a handy tool when you are doing equilibria problems. Now they're all gases, so I know they're all included in here. ICE. Now what do we plug into here when we're dealing with concentrations? In Kc, it needs to be molarity. Molarity is moles per liter. So I have HI given to me. They give me the value for molarity is the moles, which is 0.550, divided by the volume of my container, which is 2.0 liters, moles per liter. And that's going to give me 0.275 as my molarity, and that's of HI. So I'm going to plug that into here. Now, I really only know it to 2 sig figs because I only know that to 2 significant figures, but I'm carrying extra along and not worrying about the sig fig values until the very end. I see that that was injected into the reaction vessel. No mention of those, so they will be zeros. Now the reaction takes place. Remember, the change line is the reaction taking place. There's a 2 coefficient there. Every time 2 of these reacts, one of those reacts and one of those reacts. So I don't know how much it is, but I know there's going to be half as much of these 2 things being formed. So I have 0.275 minus 2x, x, and x. And I'm going to take this information and plug it into my expression there. 0.0156 is equal to H2, which is x, times I2, which is x, divided by HI. Oops, I forgot something. That's very important. That 2 coefficient, raise the power of its coefficient. So HI squared, so it's 0.275 minus 2x, and that squared. And this is something that I love seeing. I look for it. If something is squared on top and the bottom, then what I can do is take the square root of both sides. Now the reality is the x we get from here, this is equal to plus or minus that, but again, every time I've done this, the plus value has been the one that works. If I solve for x correctly and I look up here and say that x makes no sense, then I would do the negative. Remember, it gives you two solutions when you do this. All right, so let's take the square root of both sides. That is going to give me 0.125, that's the square root of this number, is equal to, well, the square root of x squared is x. And the square root of this squared is 0.275 minus 2x. Now, I don't have any squared terms, so I don't have to worry about the quadratic. Now, what I'm going to do is I'm going to multiply this to this side and do the distributive property. Let me write it out, what I'm doing, okay? So I'm taking 0.275 minus 2x, and that is equal to x. So I've multiplied both sides by this denominator. And the 0.125 times 0.275 is 0.034. 0.034, and another, I'll carry an extra sig fig. And then this times a negative 2x is a negative 0.250x, and that is equal to x. Now I'm going to combine this over here. So I'm going to add 0.250 to both sides. I'm going to come over here and work that. I'm adding 0.250 to 1, right? So this gives me 0.0343. Bringing this over to this side, I have 1.250x. And then dividing both sides by 1.250. And I will get an x value equal to 0.0275. Okay, that doesn't look very legible, so I'll try again. 0.0275. So that's my value of x. Now that we've had x, I've told you x is not necessarily the answer. I want you to go back to what you see there, and I want you to put in what is the concentration of HI at equilibrium. Well, how did you do that? Well, there is the HI, okay? This is its concentration at equilibrium. So I would take 0.275 minus 2 times my x value, okay? And that will give me the value of my HI concentration. And I have a value of 0.22. What are the units? Well, it's all in molarity, okay? So when you get to x, make sure you don't think that that's the answer. I mention that because over and over again I see students missing exam questions, getting frustrated with their homework, not because they can't do the beautiful work, because when they get to the end, they don't actually go back and say, well, what am I trying to calculate? So just be careful, and you won't have that problem. Okay, so I was telling you we want to try to avoid the quadratic at all costs. I'm going to teach you another thing to look for when equilibria are involved and you're trying not to have to use a quadratic. When k is very small, okay, we can do a nice little trick that gets rid of that quadratic, that x squared term. Now, by very small, typically we're talking in the magnitude of 10 to the minus 5 or smaller. So 10 to the minus 6, 10 to the minus 7. That is kind of the, in general, cutoff. You could try it if it's a little bit bigger. If it's a lot bit smaller, absolutely it's going to work. But this is kind of the borderline. Let's just think about what a small k tells you. A small k tells you that equilibria lies far to the left, okay? And that you have a lot more reactants. And if you started with all reactants, it wouldn't proceed very much towards products in order to reach equilibrium. There are far less reactants than there are products. That's what we learned about the magnitude of k. So we're going to use that information to solve some problems. So let's look at this one here. I have this reaction and they tell me what the k value is. Let's write the expression. K, and what are we working with? We're working with a Kc, so we're in concentrations. It would be the concentration of I, that's just the atom I, squared, divided by the molecule I2. Now when you heat this up to a fairly high temperature, it will form some of the atomic I, okay? So it will go to products a little bit. You have to heat it up to 1,000 Kelvin to get it to do this, but you can make this reaction, reactions proceed to form products. I know the value for this is actually, let's get rid of that number so I don't get confused by it, 3.8 times 10 to the minus 5. So let's see that 10 to the minus 5, I think, well, maybe it'll work. I'm going to write my expression, my reaction. I2, it's a gas, going to 2I, also a gas, so that's why I included them both, okay? I'll set myself up an ICE table. Initially, what do we have? 0.869 moles in a 2.5 liter flask. So I need molarity to plug into this table. So I'm going to take the moles, 0.869, and I'm going to divide by the volume. It's a 2.5 liter flask, and that's going to give me a value of, let's see, 0.34, and I'm going to carry an extra sig fig along for the ride. I really only know it to 2 places. Okay, so now I can plug that into my table. That's all they said they put in, so there's no 0 here. Now in every one of my examples I keep putting a 0 on the product side. You don't necessarily have to start with all reactant and no product. You can start with some of both. You could start with only product and it proceed this way. You don't have to rearrange the reaction. You just realize that I'm using up on one side and producing on the other side. But that's been kind of a typical scenario we see here. All right, so some of this gets consumed. I don't know how much, and what am I going to put right here? Well, that 2 tells me I have 2x there, so I have 0.344 minus x, and I have 2x. So I'm going to go to my expression, and I'm going to plug in what I have here into what I see up here. I have the value 3.8 times 10 to the minus 5 is equal to 2x, but that's squared, divided by 0.344 minus x. And here is where the trick comes. It is a legitimate thing to do, okay? If we think about this equilibrium and the very small k, that means not much product is formed, very little of I2 gets used up. So we're going to make an assumption. We're going to check this assumption and make sure it's not bogus to assume that. We are going to assume that x is much, much smaller than 0.344. And if I make that assumption, I can say, well, if it's so much smaller than 0.344, then if I were to subtract it from 0.344, we would still have 0.344. So I'll use this little proofreading mark that says delete. I'm just taking that out. Okay, now let's just talk about the legitimacy of this. Wednesday, I'm going to get a haircut, okay? I'm going to get a haircut, and I have a certain amount of mass, and I'm going to cut off my hair. Now the question is the amount of hair I'm cutting off significant to where it makes me weigh less? It is a weight, it is going away, it is being thrown away. But if I get on the scale before and after the haircut, I can assure you I did not lose weight, okay? That's what happens when the amount you're losing is very small compared to the amount you have. It doesn't change the value. So let me make up a number. What if x ends up being 0.0000001? If I take 0.0000001 and subtract it from 0.334, would I still get 0.344? Yes, I would. So that's the legitimacy of it. We'll check that it was okay once we solve for x. This keeps me from having to do the quadratic. So now I have 3.8 times 10 to the minus 5 times my denominator, getting it up here, okay? And that is going to be equal to 2x squared, which is 4x squared. The 2 and the x are both squared. So when I multiply these two values together, I will end up with 1.31 times 10 to the minus 5 Okay, I will divide both sides by 4. Okay, what will that give me? When I divide both sides by 4, I get 3.27 times 10 to the minus 6. Okay, now it's quite easy. I divided both sides by 4 there. Now I take the square root of x, and truly it'll give me 2 solutions, but I only need the positive one. That gives me an x value of what? 0.0018. Okay. Now you might see some books that say things like, as long as this is less than 5% of the magnitude of this, it was a legitimate thing to do, and you could do a check that way. But I like to check it pure and simple by saying, well, was it so small that it really didn't change the value? When I keep in mind that this is only 0.34, I've just carried that extra 4 along for good measure. If I take 0.34 and I subtract 0.0018, guess what I get? I still get 0.34. That's my check. It was so small that it didn't make any difference, so I ignored it, and that was a fine. So you always do the check, because it's not always going to work to make that assumption. But if you do the check and it was okay, you're great. If you do the check and it wasn't great, what would you do then? Well, you go back and put that x back in there, and you do the quadratic. Or, here's another option. I'm going to talk you through it. You could take the number you came up with and plug it in for x. This x here only, and say, okay, it's not really 0, it's a little bit, now put it in there, and then solve for x again. Do that a few times until your x value doesn't change. I'll do anything to not have to do the quadratic again, and that is successive approximations, okay? So, moral to this story is, you want to be on the lookout for k's that are small. K's that have a high negative value here. 10 to the minus 5 is a good value, or 10 to the minus 6, 10 to the minus 7, anything smaller than 10 to the minus 5. When that happens, you are saying not all x's are negligible, but the one that is added or subtracted from a value is negligible. So you're assuming this so you can take it out, and that gets rid of you having to do the quadratic equation. All right, so now you have seen a whole bunch of different example calculations. We did several where we're trying to determine the equilibrium. Oh, by the way, are we done? We're not done. I should back up. I did all that rigmarole, and I did exactly what I told you all should not do. What did the question ask? Did it ask me what x is? No. It says, what's the concentration of the gases at equilibrium? Okay, so let's at least finish this up. If I take 0.344 and subtract 0.0018 and keep it to 2 decimal places, I will have 0.34. Okay, because 0.0018 still gives me 0.34. If I take 2 times 0.0018, I will have the concentration of I at equilibrium, and that is 0.0036. What are the units? Molarity and molarity. Okay, so now we have officially finished this problem. And back to what I was going to say, giving you lots of examples of how to solve for equilibrium concentrations if you know a value for K. We've seen several examples. Every one of them used an ICE table. At the very first problem of this unit, I didn't know the K, but I knew information that I could plug into my table to obtain a K. Those are your 2 big main calculations in this chapter. Can you go between equilibrium concentrations and K, or K and get equilibrium concentrations? This is the end of our whole unit on chemical equilibria, but we're going to look next at how to do all of these same type of calculations in the environment of acids and bases.